Okay. So today we'll review AX equals B. And like I said, we're not going to talk about the details of Gaussian elimination. We're not going to talk about the strategy of finding the solution to AX equals B. We're going to talk about the interpretation of AX equals B. The structure of AX equals B. The structure throughout this course and in life and in all aspects of science. The structure and the insight are much more important than the nitty-gritty details. So let's talk about the structure of linear systems AX equals B. And there are three different ways to interpret it. There's the row interpretation, which I'll dismiss, undeservedly so perhaps, the column interpretation, and then the operator, or linear transformation interpretation. And the first, the row description we'll dismiss as irrelevant to this course. Column interpretation is very important, especially if you think in terms of bases and linear decomposition and all of that. The column interpretation is the dominant one. But even more important, in some ways even more basic, is the linear transformation interpretation. So let's make the discussion a little bit more specific. What we're talking about here is a system of linear equations written in matrix form. So A is a matrix, and it is probably wider than it is tall. So we have few equations and a lot of unknowns. So the chances are it has a solution, because there are not too many conditions for the number of variables you have. You have all these variables, and only if you think of equations as constraints, so only a few constraints to satisfy. So this is underdetermined. So likely there is a solution, and if there is one, and there probably is, there are definitely infinitely many solutions. That's the mode we're in, and I will draw it like this. Do you see? It is wider than it is tall. That's the shape of A. Okay? And then there are lots of unknowns, so the column of unknowns will be taller than the matrix. And then there's a right-hand side, and that's B. Okay. Let's talk about the three perspectives. The row perspective. Excuse me. All right, the row perspective is basically thinking of the system of equations as a collection of equations. So you would look at it one row at a time, and if you recall, a row corresponds to an equation. And so you will say, all right, we have all these variables, and we have to satisfy this condition, and this condition. So you interpret what you're looking at as a collection of equations. That perspective is completely irrelevant to the subject of differential equations, and I would even say to math in general. Although interestingly, when you go through the details of solving the system, you operate on rows. It's row reduction. Gaussian elimination is a row-wise algorithm. So actually, I take it back. It's not that irrelevant. It's just that it's more a matter of solving the system. We want to talk about what it means. We're deep people. We want to talk about what it means. So first, we'll talk about the column-wise perspective. Excuse me. In the column-wise perspective, you think of linear system AX equals B as a linear decomposition problem, where you have to decompose the vector on the right, we'll call it B, as a linear combination of the columns of the matrix. So we'll think of the matrix as a collection of columns for C1, C2, C3, C4. This is B, different color. We have the luxury of colors, might as well use it. And here is B. Okay, so we have 4 columns, C1, C2, C3, C4, and a right-hand side B. And as you know, solving this system of equations is equivalent to expressing B as a linear combination of C1, C2, and C3. And I would write it like this. And C4. I hope that fits. Okay. And your unknowns are these coefficients here. And so what could happen in this situation, a variety of things. I will illustrate with an example. I will actually pick a specific matrix with specific numbers, which will give us a specific system, and we will solve it without ever referencing Gaussian elimination. And that will be something that I will expect you to be able to do for next week's quiz. And it's very important that you absolutely do not need Gaussian elimination. I will try to never have you face a system where you actually need Gaussian elimination. Sometimes I won't be able to avoid it. That's life. Sometimes you end up with a system, and if you understand the structure, sometimes you have to do the work, and that work involves Gaussian elimination. But it's secondary to understanding the structure. So here's our system. Heck, I'll make it complicated looking. Okay, take it in. And the point that I want to make with the numbers that I selected is that this system is nearly trivial if you understand the structure, and very unpleasant if you don't. So let's do a quick show of hands that will not appear on YouTube at all. Who thinks this is a gimme? Raise your hand. Okay, and who thinks, whoa, I wouldn't want to see something like this on a test? Okay, so probably the rest of you. Okay, good. So, yes, this is a complete gimme. And that's the beauty of understanding the big picture. So let me now just take a moment to copy this over to the right-hand side so I can talk about vectors and not columns in a matrix. Okay, and here comes, so this is X, this is Y, this is Z, this is T, and here is where we'll summarize the solution. X, Y, Z, T. X, Y, Z, T, and I might as well write the equal sign. Okay, so here it is. Solving this system is equivalent to solving this decomposition problem. And I think that one of the relationship, and of course it's all about the relationships. I'm a modern man, I love talking about relationships. It's all about the relationships among the vectors. Linear relationships, it's how this vector, the target vector, is related to the decomposition vectors. And I think that my choice of numbers has made it quite obvious. Do you see how I can get this one out of these two by a careful choice of numbers? This vector is, well, tell me, what linear combination is it of these two?
1 and 10.
I'm sorry?
1 and 10.
1 and 10. 10 of this one to give me 70, 80, 30, and 1 of this one to make it 71, 84, and 33. So that's one possible solution, so let's write it down. One possible solution. What is it? 0, 1, 10. Okay? One possible solution. It's called a particular solution, because that's what it is. It is a particular solution. One specific solution. A particular solution. The article is very important. It so happens that you can choose any particular solution that you want. And that makes life actually very interesting, because depending on what particular solution you choose, the expression that captures all the possible solutions will be different. So you're in a subject where the answer is not a particular expression, but the collection of vectors that that expression represents. And so you can choose any expression you want as long as it represents the right collection of vectors. So a particular solution, that's what this is, and that's a legitimate part of the solution. And as the theorem will go, you can choose any one whatsoever, and they're all equally good. Now, the important thing here is that it's not the only solution. There are very many. And we have to capture all of them. We have to capture all of them. And the key to capturing all of them is identifying the null space. The null space has to do with the relationship among these vectors. You see, a particular solution has to do with the relationship of the target vector to the decomposition vectors. But the null space has nothing to do with the target vector. It's all about the relationships among the vectors. And what you notice there is that, let's step into linear algebra, these vectors are linearly dependent. How do we know that they're linearly dependent? Well, there are 4 of them in a 3-dimensional space. So they're linearly dependent. Even if you didn't see the relationship, you would know that they're linearly dependent. Okay, but we actually need to know the relationship. We need to know the specific way in which they're linearly dependent. And the giveaway is, of course, here. This vector is clearly, I made it easy to see, 10 of this plus 1 of this. So if I take 10 of this and 1 of this, I get this one. Which means that if I take 10 of this, 1 of this, and minus 1 of this one, I will get 0. It's a fancy combination. Fancy is a fancy word for non-trivial. It's a non-trivial combination that produces the 0 vector. And so if I add that mix to a solution that I have already chosen, on the one hand, it won't change the fact that this combination will produce this target vector, because all I did was add 0. So on the one hand, it preserves the fact that the new combination gives you this vector. On the other hand, it's a new set of numbers, so it's a new solution. So it's more than a step in the right direction. It's the exact right thing to do, which is throw that into the mix. So 10, 1, 0, minus 1. Right? So this is a particular solution. This guarantees that if I take these vectors in these proportions, I will get the target vector. What this does is, on the one hand, preserves that, because that's a combination that gives 0. So it preserves the fact that these new numbers, 10, 2, 0, 10, 2, 10, minus 1, will still produce the target vector, but it's a new solution. And that's my goal, is to list all possible solutions. So then you say, well, if this produces 0, I could add 2 of these vectors. And it would still, the overall sum will produce the target vector, but it'll be a new solution, or 3 times, or minus 10, or pi, or alpha. Or alpha. And now we have captured all possible ways of doing it. And so whenever you have AX equals B, the solution always looks like a particular solution plus the null space, denoted by the letter N. So the solution always has this form. A particular solution plus the null space. I'll mention something interesting. I won't. I'll mention it, but I'll edit it out. For those few of you who were just in my previous class, doesn't this look like exactly what we talked about at the end of the class, where we're talking about the equation of a straight line, where we chose any one vector to get to the straight line, right? It kind of looked like this, right? We chose a particular vector to get to the straight line, and then we had a coefficient alpha, and then there was a vector that moved us along a straight line. So do you see, it's not at all a coincidence that this is an entirely identical structure, right? An arbitrary vector that gets you to where you need to go, and then a coefficient that moves you around in a certain direction, right? 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 Yeah, it's cool. Okay, but pause for editing. Okay, so when you were taking your linear algebra class, there were lots of details that you had to worry about. They were, which particular solution? The answer is any particular solution. But then a more interesting question was, you know, how do I know that I have captured the entire null space correctly? How do I know how many of these vectors to have? Because sometimes it's plus alpha times this, you know, plus beta times another vector, potentially plus gamma times another vector, and so forth. There were some examples where there were 7 of these. So how do I know how many there are? Very important question. Took a long time to discuss. Then there was another question that was, well, if I can't see these numbers, right now we just did it by insight. But if I'm not able to simply guess them, what do? And the answer was Gaussian elimination. Row-reduced echelon form. Very robust techniques for doing it. That was another couple of weeks. So there are lots of details here. But what I just summarized exhaustively is that the solution will always look like this. A particular solution, one way to get the target vector, and then because of the relationships among the columns, the entirety of the null space. Okay. And I can actually prove, and I will prove it in just a moment when we use the linear transformation perspective, that this is actually, that an expression like this captures all possible solutions. Okay, so now we'll talk about the linear. Are there any questions about this? No, we're good? Okay. Before I switch gears, practice this. Practice this. There are lots of examples on lemma. I'll provide the links. But you should be able to do this for any matrix. In class today, I'll do another example, a couple examples You know, you'll never have to do Gaussian elimination, unless by accident. Okay, so now we'll talk about the linear transformation perspective on this, which is actually more relevant to partial differential equations, especially the way we'll start working on them. So I will erase everything except this, because I'll show you from the linear transformation perspective that this still holds. Here we go. Here's our new interpretation. We have two spaces, Rm, actually Rn, and Rm. And we have a transformation from Rn to Rm affected by this matrix. So here we have, like this, m equations and n unknowns. So you should think of the variable x as sitting in Rn because there are n unknowns. That's how tall x is. And when you multiply it by the matrix A, it becomes a vector from Rm with m entries. So we think of A as a linear transformation or a representation of a linear transformation. Let's say more literally linear transformation that sends vectors that are n entries tall to entries that are m entries tall. And so for any vector, you can find its image. What do? You simply multiply it by the matrix A. And that will produce a vector with m entries from Rm. We're good? You see the, what do you call it? The logistics of what's going on? Yes. But the question now, the interesting question, is that of pre-image. If I tell you the resulting vector, B, where did it come from? Right, everybody can easily do the forward transformation, but the inverse is of course impossible because this space is much richer than this space, right? N is larger. So there will be two vectors that go to the same image. It'll be onto, but not one-to-one. I mean, I've never used these words before in my life, but I think I used them accurately. Right, so two vectors, actually infinitely many, will go into the same vector B. So when you ask me, under this transformation, what goes to B? That's what this is asking. Given B, what goes to B? What this is saying, before you interpret it as a system of equations, is given x, A sends x to AX, and it becomes B. But now if we interpret it as a system of equations, that is given B, what x gets sent to it. So that's the linear transformations perspective on the system. It's the question of the inverse linear transformation, especially in the situation where this clean one-to-one inverse doesn't exist. And so you have to capture the totality of vectors that get sent to B. And this perspective there, I've actually told you the entire perspective. It doesn't help you solve it. It doesn't help you, I guess it just doesn't help you to solve it. Yes, it's just an interpretation. But in this interpretation, the great advantage of this interpretation is that we can use matrix algebra or operator algebra, whatever you want to call it. We can make arguments based on algebra. And it is based on algebra that this will be particularly easy to prove. So what I will prove to you right now, without telling you how you might solve this inverse problem, is that the answer will always look like this. And that is, you have to find any one way of doing it. So any one vector that goes to B, and then add to it the null space. let's talk about what the null space means in the context of linear transformations. The null space, here. What's the null space in the context of linear transformations? I'll write it. Null space. I'm a big fan of using, if it started out as 2 words, I like keeping it as 2 words. It's the null space. I think it's more common to write this as 1 word, null space. But then it sounds like Microsoft. It sounds like 2 arbitrary words put together. And even though I'm not a native speaker, and I don't really have a right of preference, I do have a preference to just keep it as an adjective and a noun. It's very nice. It's a space. Which space is it? It's the null space. It's nice. Null space in the context of linear transformations. Well, here it is. A vector n, so it's denoted by capital letter n, and a little vector n, not little vector, vector denoted by the little n, belongs to the null space if an equals 0. That's the definition of the null space in the context of linear transformations. And it will be up to you to mentally connect. You always have to do it for yourself. This definition of the null space with the way we just treated the null space, which is the space really, of all linear combinations of columns that produce 0. You have to sort of say, oh yeah, I can see how through the mechanics of matrix multiplication, it's one and the same thing. You have to sort of make sure of that, or talk to me about it. It's hard to explain. You can get it in the course of a conversation. So if you're not 100% certain of it, we'll talk. But that's how it's defined. an, if an equals 0, then n is in the null space. So this gives you a criterion. Once again, it doesn't tell you how to find the null space, but it does give you a criterion for a particular vector for deciding whether it's in the null space or not. You multiply it by a, and if you get 0, it's in the null space. So it's pretty good definition for, it doesn't give you an algorithm for finding n, but it does give you an algorithm for testing whether a particular vector is in the null space. And that's enough to prove lots of things. Well, first of all, it's called a space, but is it really a space? Remember that to be a space, you have to be a space. You have to be closed under addition and multiplication by a number. So in other words, if there are two vectors, and each one is in the null so-called space, will their sum also be in the null space? Very easy to check. Suppose I'm told that n1 is in the null space. Well then an1 equals 0. Suppose I'm told that n2 is in the null space. That means that an2 equals 0. The question is n1 plus n2 in the null space? Let's test. How do I test? I multiply that sum by a. A times n1 plus n2, well, I know it's distributive. If you think of it as matrix multiplication is distributive. If you think of it as just a linear transformation, which is a better way to think about it here, whatever linear transformation, then this distributes by the very definition of what it means to be a linear transformation. That's what it means. It means it distributes its arguments. It will be an1 plus an2. And so we have 0 plus 0 equals 0. Trivial math, non-trivial content matter. But what you have on the board here is proof that if n1 is in the null space and n2 is in the null space, then n1 plus n2 is also in the null space. And you can do the same thing for multiplication by scale. You can prove that if a vector is in the null space, then a number times that vector is also in the null space. And so it really is a space. So that's very important. It really is a space. Great. So that's the definition of the null space. I'll repeat myself a third time. it doesn't help you identify the null space. It just tells you what it is. And it's a very clear thing. It's the set of all vectors that this transformation sends to 0, and we just proved that this set of vectors constitutes a subspace of the entire space. It really is a space. So that's great. I will now prove that the solution to this problem, in other words, the problem is, given a vector B, find all vectors that go to it. Theorem. That's the problem. Here's the theorem. All of these vectors can be captured by the following expression. It's any one way of doing it, an arbitrarily selected one vector whose image under A is B. So in other words, it's any one vector such that under A it goes to B. That's the definition of X sub P, and it's called a particular solution, and I'm not telling you how you would obtain it, I'm just telling you pick one. Any one. Pick one, any one, and stick with it. And then add to it anything from the null space. So think of this as an infinite collection of vectors, the whole space. And what this is telling you is that when you take all of them one at a time and you add them to the one you chose, you will get your new infinite set of vectors, and that will be all the vectors that A sends to B. That will be all the vectors that A sends to B. Proof. Do you guys understand the statement? Let me repeat the statement. I think it's sometimes just straight repetition helps. What I'm saying is that if you choose any one vector that happens to go to B under A, and you add to it in turn, one at a time, all the vectors from the null space, you will be having in turn, one at a time, all the vectors that A sends to B. Proof. First, so what do I have to prove? I have to prove that any vector, that number one, the vectors that I just described all go to B, I have to prove that. And I also have to prove that they're all such vectors, that I didn't miss any. So I have to prove that I don't have any rogue vectors in there that for some reason don't go to B. And I also have to prove that all the ones that do go to B are among these vectors. Okay, so one of them is easy and the other one is super easy. So we'll start with a super easy one. I will prove that any vector that has this form, our arbitrary choice plus a vector from the null space, goes to B under A. Proof. Let me call that vector, let me choose a particular one. No, again, I don't want to reuse the word particular. Let me choose one. I'll call it little n. I'll call it little n. So I'll take my arbitrarily chosen particular solution and I'll add to it any member of the null space. Let me prove that A sends this sum to B and nowhere else. That couldn't be easier. This is the super easy one. A, well, let's apply A to it. You guys do it on your own. Take 10 seconds to do it on your own. Just plug it in and see what you get. Will you get B? Will you? Will you? Yeah, you will. Try. Okay. So actually, this is my favorite kind of math, where the stuff you're writing on the board looks like third grade stuff, right? It looks like we're using the distributive law. But what's actually happening, the thoughts that you're having that this is representing are actually quite advanced. That's how most things happen. Or at least you always aim to reduce whatever it is you're working on to that, sort of simplicity of notation. So let's see. I'm applying A to X. Of course, X is the sum of these two things, so I'm applying A to that. It's just substitution. You can call it the distributive property of matrix multiplication or the definition of what it means to be a linear transformation. You can apply A to X particular and A to N. And of course, the way we chose a particular solution is just one way, any one way that produces B. So lo and behold, that produces B. And N is in the null space, so that produces 0. So the result is B. So yes, anything that looks like this, goes to be under A. And even though the context of our discussion is very different, do you see the parallel to what we talked about, how we have a linear combination of things, a special collection of coefficients that produce the 0 vector, and so they don't change the fact that we get the target vector? Well, you're kind of seeing that here. There's that combination, right? It does alter the way the vector looks, but ultimately doesn't change the fact that we get B. So totally the same thing in an entirely different context. Okay, so that was the super simple part. Although I think that it's these super simple things that when sometimes you read in a book, the derivation looks so trivial that it actually totally throws you. That's always been my experience. The simpler the proof, the harder it is to see the point of what's happening. So it's much more important, you know, what your starting point is and what your target is much more important than the actual expressions on the board or on a piece of paper, which are so simple, you know, that's just my experience. Okay, now comes the simple part. Meaning, we covered the super simple, now it's the simple part. Again, the math will be trivial, and it's the thoughts and the words that happen outside of the math that we're writing down. And it's the, you know, and it's really knowing, keeping track of what's given, where we're going, what are we doing. That's the meat, the essence of what's happening, not what I'm writing on the board. So suppose that Y gets sent to B by A. I want to prove that Y is necessarily that Y can always be expressed as the arbitrary particular solution that I chose, totally arbitrary. I just found, somehow I found one vector that A sends to B. That's all I did. And now I'm saying that any such vector can be expressed as my arbitrarily chosen vector that does that, plus something from the null space. You know, if I just left you here, I don't know how many of you would actually be able to do it. I wouldn't be able to do this when I was in college, for sure, because you kind of get, it seems like an overwhelming statement, because nothing's given. Nothing specific is given. Right? I didn't tell you how I chose my particular solution. I didn't tell you how I chose Y. So how do I go from Y that I don't know much about except that you get B to my particular solution, which I also don't know how it was chosen or anything else? Right? So it's kind of one of those vague situations. But here's how you deal with it. Let's think about Y, the vector I'm told goes to B under A, and I subtract to it, I subtract from it my arbitrarily chosen particular solution. And let's see what happens when I apply A to this difference. You tell me, what will happen when I apply A to this difference? It's almost like I don't know what to do, so I'm doing the one thing that I can. So I have Y, I don't know where it came from, but I know that it produces B. I have my own particular solution. I don't know how I got it. All I know is that it produces B. So I'm doing the one thing I can. I'm subtracting them. I could have added them. But, so okay, so I'm doing one of two things I could. I'm subtracting them. And then I'll do the next one thing that I can do, which is apply A to it. I'm in a context where all you can do is apply A to it, because I don't have anything else at my disposal. So let's see what happens when I apply A to this difference. Yeah, I'm telling you. Yeah, I'm telling you to do it. You can just throw out the answer? 0. That's right. But it takes a couple steps to get there, right? You have to do the distributive law. Yeah, so let's do it. At every point, you do the one thing you can, and everything works out. And it seems trivial, except the logic behind it is not. So using the distributive law is it becomes AY minus AXP. Great. We know that this produces B, and this produces B, so we have B minus B. So we have 0. So this vector goes to 0 under A, which means it belongs to the null space, which means that Y minus XP, I'm just writing down what I just said, belongs to the null space. It's in the null space because A sends it to 0. It's in the null space. So some element in the null space, I'll call it little n. So we have Y minus XP, we just proved, must equal little n from the null space. And so Y equals XP plus n. And so what we proved is that any vector that gets sent to B has the form our arbitrarily chosen, oh sorry. So at this point it's plus little n. So what we have proven is that any number that gets sent to B by A can be represented as our arbitrarily chosen particular solution plus some vector from the null space. So it also has this form. So with regard to this form, we have proven two things. One, that anything that has this form goes to B, so it's a solution to this problem. And then everything that goes to B has this form. So this captures all possible solutions to the question of inverting the effect of this linear transformation. And that's the linear transformation perspective on solving linear systems. Kind of beautiful the way it happened, where you start with a linear system, you write it in matrix form, and then you start thinking of the matrix as a linear transformation. Kind of nice. Not the way I think of linear algebra, where linear transformations happen first, and then you represent them by matrices. Here, it's nice. You go from a matrix to thinking of it as a linear transformation. Beautiful, really. Okay, but whether you take the column perspective or the linear transformation perspective, the conclusion is the same, is that all solutions to this kind of problem are represented as a particular solution plus the null space. That's it. This completes our review of AX equals B from two very important perspectives for applied mathematics. Now let's just do just a couple examples so that you know what I expect you to do on the test, okay? Okay, let me review this solution. So, the pattern is you have to find a particular solution. One way to get this out of this, and of course I gave you a couple really good vectors to work with. So you take 3 of the first column minus 5 of the second, none of the third, none of the fourth. You get your right-hand side. Good. That's this guy. So you have found your particular solution. You're done. You don't ever have to find another, because the theorem says that any one works as well as any other. Great. Now you have to capture all of the possible relationships among the columns. And so you notice, of course, that this one is 3 of this plus 4 of this. So 3 of this plus 4 of this produces the third column. So subtracting the third column, 3 of this plus 4 of this minus this produces your 0, so it's in the null space. And there you go. I'm sorry, that's one element of the null space. And then you do the same thing with this column. 2 of the first, 7 of the second, ignore the third, subtract the fourth, and that's the other element of the null space, and you're done.